Yeah, hi, thank you. Yes, my name is Ted Selig. I really appreciate everybody's time to listen, and I'd like to tell you about what we're doing in the area of real time and HDF, and hear challenges that you all see, and exchange ideas. Um, I do want to confess up front, I've had a couple deadlines and haven't been able to sit in on all the chats. I've done a couple of them, so I have some homework. I see the record button on, so I hope I have access. HDF5 group's going to let us listen to some of these because I want to catch up with my homework. So and really excited to be in this with this group. I think we're brothers and sisters here in scientific data. Excited about that, and just want to tell you about what we work on. We work on embedded systems. It's kind of our world. Work on radar systems, a lot of for defense, and these things we've been working on for probably 20 on years. And software, FishEye is building the software for these systems. They're mission critical. They work at like radars that work with speeds that approach the speed of light. And FishEye engineers have been building the brains of these systems, integrating subsystems together, deploying them around the world, simulating their environments, and sustain and maintain them once they're operational. And there's a lot of common characteristics in this. There's a data tsunami, just overflow of data, big data. It's often difficult to access the data, very technical, complex systems to share and exploit. They're time critical, and perturbing them can have them cease to operate, so it's hard to look at them while they're running. They're often operate in real time, but they are debugged in batch, kind of after the fact, which slows the process down and hard to see effects as they're happening. And then there's a big need to compare over time. So doing things like regression, running and seeing how they run, comparing results as you make software changes and system changes, and also doing things like Monte Carlo, running them over and over again to see how they behave. And these challenges extend over the life cycle, the entire life cycle of the systems when they're developed, integrated, test, when they're maintained or sustained, and when they're operated. And that's why it brings us, FishEye, to HDF group and our long interchange with HDF. A lot of the benefits that technology brings goes well with this heterogeneous systems. There are all kinds of computers, different representation of data. There's a big need to simplify and ease sharing. It's often system or project specific data. There can be a mix of going between Indianness and platforms. It's very fast, which creates big data. And there's big benefits in keeping data with metadata. And so we call this quest our FishEye's mission to liberate this difficult data, enable simple analysis and machine learning for powerful decisions, all happening in real time. And we're guided by some principles. We favor egress, getting data out of the system efficiently over putting data in. So you think of, again, I talked about, like, you don't want to perturb, or we want to be minimally intrusive on these systems while we instrument them. And unlike a database maybe is optimized to do queries, we're always optimizing to just quickly tap off and see the data. And another kind of principle is we embrace machine data. So we, as a mantra, try and work with the data as it is and not convert it, because that takes time. Converting machine data to ASCII that the web world might do actually takes a lot of computing power. and it makes the data bigger and it slows everything down. So we embrace machine data as it is. And we also plan to expect overflow and just a ebb and flow of data. And we seek to simplify. This world is so complex, you know, any kind of software is very complex. So it's always in our interest to try and make the process easier. And then we try and create information in real time from the data. And so you can understand what's going on and quickly make changes and work with the systems in the time that it does, you know, real time. And this is kind of all our overall mission of synthesizing the world's real-time data. And we embody this in a platform we call the FishEye real-time platform. And just to give you an overview, it takes in information, data from things like sensors, command and control, weapon systems, simulators, through kind of a capture interface. I'll show a little bit of that. And one unique capability that also I want to show and get your thoughts on is a metadata injection process. It's a process where we automatically go into programs and software and get the schema, the layout of that data, and kind of bridge that into HDF automatically. And that process is done before you run. And what it does is enable the platform to do things like analysis in real time. So we have a complex event engine that will let you analyze that data as it flows through. We use that engine to curate so we can pull out just the most important nuggets, the needles out of the haystack, and get rid of all this extra data, all the chaff that never will get used, which will save the time that you in runtime, be more efficient in network usage, in storage, and then ultimately plowing through that data, analyze it after the fact. And then in our roadmap, we've been working on some capabilities, which again, I hope to team with HDF, and the technology here is the data lake capability, the capability of storing data over successive runs to enable cloud. I think there's a lot of good HDF technology and supporting cloud objectives and kind of disconnect the challenge of infrastructure. And then there's a big demand for machine learning, and I think this platform lends itself to that, where we can build up pipelines of data for training of machine learning and then predicting. We're working on developing technology which takes streams of time series data and forecast its future values for things like prediction, prognostics. And we're actually using it in our curation, so we are able to change the data collection valves ahead of time before there's a bow wave of data that causes critical loss of data. This is all customized for target applications. And this is got HDF inside. It's a core to the technology and interface, a big part of it. And how it works is technology into the platform comes in through files, through application interface, or through network connections. And the interface takes both data and metadata, that kind of metadata injection process. And then there's the platform in the middle that lets the curation, the flowing analysis, and we call a routing service where you can route the data for different applications. And one is real-time HDF, so we can be writing to HDF and looking at, and another is getting to analysis and reporting, and in Python, like some of what Thomas was showing, and all that happening, getting that to work in real time. So all these, plugging these pieces together to work in real time. And some of the enabled technology is, you know, usually a developer will create some code, a compiler, and make an application. There may also be ways of structures for networking. And this technology, MetaGen, goes in and looks at machine code and source code and pulls out the metadata and is able to put that into HDF file format. And then when the system runs, we can just simply put the data in, and we've captured the metadata automatically. And the idea is that, as you all know, you can do analysis, a simplified analysis process from there. And this approach makes it very simple. It kind of eliminates the homework of updating your data and modifying it. It makes it very fast. It's all automatic. It's portability of HDF between hardware platforms and such. And it's open, so you don't need project-specific systems. And so just an example of the demonstration put together is, so there's a program, a sensor, collects data, the developer makes some sort of structure in C++ or some other language. We have Java and Ada, and take this data, and as they would their natural system, and they put instrumentation spots in. I'm going to show the code for that. Here's a little example code that we put up for this demonstration, and that code goes through this API call. You actually pass in the C++ name of the structure. You title it, you give it a name, the user gives it a name, or the developer gives it a name, and you give the object file where that code is located. And the metadata function goes in there and it pulls out the schema and the layout and builds the HDF5 schema from that directly. And then next you define, give it an ID. The developer gives it some sort of ID. You give it a name or a number. And then you start, we have a microservice architecture. You start up that architecture with a call, give it the dictionary. And then finally, the application makes some data. It creates it just as it would naturally. And then finally make a little call where you give the address and the length of that call of the data, and it takes a snapshot, copying it out, very high performance, quick memory copy. And then finally, when you're done, the system shuts down, you call and shut down the real-time platform. And so what I'm going to show next is that was the data going in through that API. And I'm going to show, we ran a little demo and show it coming out to HDF5 and also this reporting to Python simultaneously. On the left is the Python representation of the data, and on the right is we're starting the demonstration and spitting out the data in real time. And we're writing H5 watch on the right, and we're looking at this data as the system writes into HDF5. And on the left, we're seeing the Python update the data and see the data as it's streaming by. So the idea is that this, I like the analogy. I was thinking about Harry Potter when you're looking at the newspaper and the pictures in the paper start to move. And really that's the vision I see, is that this data becomes alive and jumps out of the page and becomes movies instead of static reports. And I think that's like movie-like analysis is where we like to go and leverage HDF. And do a lot like what merge together what Thomas was showing with the live data. And so just to review this, so the API was calling in data, it was sending both metadata and data. It was going in, it was getting routed to HDF. We were writing H5 watch so you could see it as the data was going in. And you were seeing Python that was getting interrupted and updated with data as new data flowed in, and all that was happening in streaming real-time method. And so the question is, so what? And I'm sure this resonates a lot with all you. You've seen these challenges and benefits, is that this idea of just totally getting rid of the batch process, which is typical in our industry. They will either record an ASCII, which is, you know, this process in HDF is 120 times faster in one of our demonstration tests than writing out ASCII IO. And it doesn't account for the computational cost of converting binary to ASCII that might go through HTML or some other JSON ASCII formed data format. And that lets the tempo of this analysis, this reductionless concept, happen at 4 times. So in a day, instead of doing 3 cycles, we could do 12 in a day and just really accelerate what's going on. and it improves innovation and productivity. We sustain some large complex radars, and some of these radars, a typical analysis, crunching the data stored in platform specific data, we convert it. It takes 5 hours typically, but some of them take 12 hours. And when we have limited time on the system to use it, that time is very critical. And when we're doing sustainment, we're doing it over and over again, so it's costly. And with this approach, we can get 12 hours to 0 or maybe 5 minutes if there's some final processing that needs to be happen. It really improves our productivity on sustaining and maintaining and innovating these systems. And then with a curation, this intelligent dynamic data logging capability, with being able to look at data, we're able to curate data at runtime. I like to quote the stat that I calculated that we are now creating 3 times the amount of data that we're able at the rate than we're creating storage. So our data production level is now outpacing the Moore's law of storing of the data. So we have to start to get smart of what we keep, and we want to do this at the edge where these systems are collected, and then only end up with the data that you need. And through this process, we can really reduce that data. So that lets us accelerate analysis. It lets us enable cloud migration. It enables this machine learning by collecting this data in a uniform way. And it standardizes real-time data infrastructure, which really just all different approaches and formats, and it really makes a complex process even harder. And we want to help simplify that data. And the idea of what we call liberating data in real time. So I hope that gave you a feel for it. Again, I wanted to just take this opportunity to explain what we're doing in our world, and like to hear what similarities are out there. Here's my contact information, and John set up a nice link with some links in here if you're interested. And please reach out to me, and I'd love to have some question and answer here. What challenges you see? We're going towards cloud. We've got pieces of it. We'd like to hear the experiences there, and what challenges are in this world. So thank you.
Thank you so much. We have probably time for 1-2 questions, please.
I have one question. In the code example, there was that piece where you did this, for the lack of a better term, reflection to sort of detect what type you are dealing with. In your overall architecture, this question of doing things at runtime versus doing things at compile time, is that an issue? Do you see, or would you like to bring more things into sort of onto the compile time, since you are using C++, sort of onto the compile time side rather than doing them at runtime?
Yeah, that's a good question. We started at compile time, and you can do this during the build process, right? Because your structures probably aren't changing. Maybe that's not the case with interpreted languages. We haven't really instrumented those because they're not real-time sorts of applications. But where it makes a difference, we have a DDS interface, dynamic data service, where the schema is broadcast at runtime, and we need to generate this transition, and we get the data type at runtime. So we could have a totally new data type at runtime. That's where it's more critical. And I think you're right, Gerd, in C++, you can actually do this in the build process and have it static. There's a slight advantage of configuration management because we have a data file that describes the schema, and you need to keep that hand in hand with the executable. And I guess it gets rid of that, at runtime. You could, while you're booting up, you could create that file, not in a tight loop. And then you don't have to, whoever's running this operating, it doesn't have to make sure these two stay in sync, which is a big challenge, right? I think that's one of the benefits is on the title page of HDF group is keeping data with metadata, and it gets away from that mantra. So there's less significant reasons, but yeah, it's a good point.